Continuing our theme on routing, in this video I'm going to tell you about the link state algorithm, in particular Dijkstra's shortest path first algorithm. This is an example of a link state protocol where the routers start by flooding to each other all the information about the topology of the network, which links are there, which links are up, which ones are down, and then from there each router is going to calculate its shortest path tree from it to every other router. Dijkstra's shortest path first algorithm is an example of what's more generally called a link state algorithm. In link state algorithms, the routers start by exchanging all of the link state. In other words, they're going to learn the topology of the network by exchanging with each other the state of the links connected to each router. So a router is going to flood to every other router the state of the links connected to it so that every router has a full topology map. And they're going to do this periodically and whenever the link state changes so that they get quick updates. And then specific to Dijkstra's algorithm, we're going to run Dijkstra's algorithm. In other words, once we've got that topology map, each router is going to independently run Dijkstra's shortest path first algorithm. If it was a different link state algorithm, then we would run a different algorithm. But because Dijkstra is so widely used, that's the example I'm going to be using here. So at the end of the day, each router finds the minimum cost spanning tree to reach every other router. Let's work through an example of Dijkstra's algorithm on this topology here. So this topology has 8 routers connected by links that are annotated with the cost of using those links. And we're going to go through the example of finding the lowest cost spanning tree from R8 to every other router. So let me just draw an example of what that might look like. This won't actually be the right one, but it will give us an example of how it might look. So it's going to start from here and maybe go out this way, go out this way, go out this way, go out this way. Maybe we're going to have this one, and this one. So that would be a spanning tree. It happens not to be the lowest cost spanning tree, but we're going to calculate that using Dijkstra's algorithm in a moment. So I'm just going to draw out how this will evolve. I'm just going to go through the steps, and then I'll take you through a more formal way of calculating it afterwards. So let's start with R8 down in the bottom right hand corner. In the first step of Dijkstra's algorithm, we're going to add the router that has the lowest cost path back to R8. And so that's R7 because it has a path of 1 back to R8. So I'm going to draw that on here, R7, with a cost of 1. Next, I'm going to look at the router that will directly connect to this tree, this little fledgling tree, with the lowest cost path back to R8. I've got two choices, either R4, which will connect back with a cost of 2, or R6 that will connect with a cost of 2. So I'm going to just toss a coin and randomly pick R6. Doesn't matter. So it's going to have a cost of 2. Next, I'm going to add the next router with the lowest cost path, and that's going to be R4 clearly. And each time I've added a router, I'm not going to consider adding it again, of course, because I've already added it into this tree that is evolving in the bottom right-hand corner of the slide here. Next, I'm going to add the one with, I've added the ones with up to a cost of 2. So is the one with a cost of 3? No, there isn't. Is there one with a cost of 4? Yeah, I've got 2 candidates here. I've got both R3 and R5. Both will connect. Okay, well, I'll arbitrarily add R5 first. That has a cost of 4 back to R8, and then I'll add R3. Do I have one with a cost of 5? Yes, I do. I've got R2. That has a cost of 5. That's cost of 5 back to R8. Do I have one with a cost of 6? Well, I've got 2 that have a cost 6, but they're already connected into the tree at a lower cost. So R3 and R4. So I'm not going to add those. They're already on the tree. But I've also got R1. I can now add that one in at a cost of 6. So that's 1, 2, 3, 4, 5, 6. I've now added them all, and I'm done. Let's go through those steps as basically the same steps that I just went through, adding each of those routers in turn. So first of all, I added R6 because it has a cost of 2. Then I added R4 because it has a cost of 2. Then I added R5 because it has a cost of 4. And then also R3, it has a cost of 4. Then I added R2, and then finally I added R1, and then I'm done. We can think of this more systematically by following through this table. So I'm going to populate this table as I go, and then I'll show you what it looks like fully populated afterwards. So this is just going to repeat exactly what the steps I just did. So I start with, at step 0, the candidate set of all those routers that directly connect to R8. So my shortest path set is going to be the set of routers that are in the shortest path tree. So I start with R8 in my shortest path set, and the candidate set are those that connect to it, directly to the current fledgling subtree. So that's R3, R5, R6, and R7, and I'm going to pick the one with the lowest cost path back to R8. That's clearly R7, so I'm going to add R7 in first. So I've chosen R7, and in which case, if I've chosen R7, I'm going to add it into my shortest path set. So my shortest path set is going to become R8 and R7. My candidate set are the set of routers that directly connect to this subtree. So the ones that directly connect are R3 and R5 still, of course, because I haven't used them yet. R6, because I haven't used that one yet. I've used R7, so now R4 becomes added to the candidate set. And I'll pick from that set the one with the lowest cost path back to R8. That could either be R4, which has a cost of 2, or it can be R6, and I'm just going to just arbitrarily pick R6. So now my shortest path set is going to be R8. I'm running out of space here, but that doesn't matter. Add R6. And my candidate set is going to be R3, R5. I've used R6, so it'll have R4 in it. And because I've added R6, well, I'm adding no more routers in now to my candidate set, so that's going to stay at the same thing. And so on. Eventually, I will fill out the table until the very last one that I will add will be in, I will choose R1 here. And so at this point, I will add 1 into my shortest path set, and then I'm going to be done. Okay? I'm going to add one router at each step. I'm going to add the router that is the lowest cost path, and because that is its lowest cost path, we know that we're done with that router. There's nothing else left to do. So it's nice and simple. We'll always run the number of iterations equal to the number of routers in the network. So if you fill out this table, you would find that it looks like this. And so you can just check that that matches what I did earlier. So if you run this algorithm, and we'll give you some exercises where you run through and fill out tables like this, you will see, and after a few times that you've done it, that, oh yes, of course, it's actually generating the full lowest cost minimum, the lowest cost spanning tree. So some questions worth asking about Dijkstra's algorithm. First one, how long does the algorithm take to run? Well, it's a nice simple answer. By the end of the kth iteration, we've added k routers to the graph. So if we have n routers to start with, it will always terminate after exactly n iterations. Nice and easy. What happens when link costs change or when the routers or links fail? Nice and easy again. Every time there's a change in the link state, in other words, every time a link goes up or down, the routers are going to flood that state to every other router in the network. They then rerun Dijkstra's algorithm, calculate the lowest cost spanning tree out to every other router, and we're back up and going again. In other words, every time there's a change, we recalculate from scratch and we move on. So we don't have to worry about the cases like bad news travels slowly, etc., that we have to worry about with the Bellman-Ford algorithm, because everything is recalculated from scratch every time there's a change. So let's see how Dijkstra's algorithm is used in practice. Dijkstra's algorithm is an example of a link state algorithm. That means that the link state is known by every router. In other words, it's flooded amongst the routers to make sure that all of the routers know the entire topology and the state of the links in the network. And then each router independently calculates the shortest path spanning tree from itself to every other router in the network. Dijkstra's algorithm is the basis of the OSPF, or Open Shortest Path First algorithm, a very widely used routing protocol in the internet, and we're going to see that in a later video. There's another way of thinking about Dijkstra's algorithm that I want to tell you about next. I first learned about this from Professor Jean Wallerand at Berkeley. And it's a very nice way to think about what's going on. So take a look at this example here with a set of routers interconnected by links, and the red numbers as before represent the cost of each link. And I'm actually going to represent them by tennis balls, the yellow routers, and a white and a pink ball representing the top and the bottom, A and B. And we're going to calculate the lowest cost spanning tree, and by connecting it by strings between each ball, where the length of the string equals the cost shown in red. So let's start with them down on the ground like this, and then if we tug and pull them up by A, each link that goes taut, or each string that goes taut, is going to be on that lowest cost spanning tree from A through the network. So eventually we'll end up with something that looks like this, where A is connected to B through R3 and R5 with a total cost of 9, and all the solid links here represent the strings that will be tight. All the ones that are dotted, the two in the bottom left-hand corner, will be slack or loose because they're not on the lowest cost spanning tree. I'm going to lift them up like this, and this is the same topology as before. So A to R1 goes tight, then A to R2 and 3 and R1 goes tight because they're all on the least cost spanning tree. Now A4 goes tight, and then R5 because they're all on the least cost spanning tree. I lift it up further, and eventually the line A, R3, R5, B will all go tight because they're all on the least cost spanning tree. And that's the end of the video about Dijkstra's algorithm.